Good day. The topic of our research is method for processing and assessing the degree of digital image compression based on a Haar transformation. Authors are Vladimir Vychuzhanin, Nickolay, Rudnichenko, Yurii, Bercov, and Andrii, Levchenko. Problem statement and relevance of our topic of research. Meeting the performance required for processing and transmitting digital images in real time and based on reducing the amount of data associated with images by compressing them. In different fields, it's a very important problem, and we need to find ways to deal with it. The use of currently known digital image compression methods allows us to reduce the time required to transfer images, to increase the number of images transmitted over the communication channel per unit of time, to reduce the requirements for the speed of information transmission devices, and reduce the storage capacity of images. Remoting sensors of the Earth's surface, as example of using unmanned aerial systems, UAC, is widely used, for example, to monitor vegetation and environmental parameters, aimed to in particular at optimizing activities in agriculture and forestry. It's a field as we can have a practical usage of the different methods of image processing. In this context, UACs have become useful for accessing crop health by acquiring large amounts of raw data that require processing for further support applications such as moisture, biomass, and others. The analysis of known works indicates a constant increase in the amount of information received from the UAC during remote sensing of the Earth's surface as an example, which outsprints the growth rate of capabilities of technical means for its processing. So in the process of conducting remote sensing data, one of the ways to solve the problem of operation, processing, and transmission of images in real time is to reduce the amount of data by compression images in efficiency ways. To transform a digital image in modern practice, according to different literature sources that we analyzed in our work, and orthogonal or wavelet transforms are used. Orthogonal transformations consist of direct and inverse transformation. Discrete forward and backward transformations in general are described in expression 1 and 2, and where we can have some coefficients like y of case conversion coefficient and the number of samples in the original signal. And of course, normalization coefficient, which may be absent in some orthogonal transformations. Our proposed method have some stages to implement it. The first step in most compression methods, and we use it to involve changing the color model. So our method deals with it too. Currently, various color models are used. The high efficiency of using of color model change as a stage of image compression is confirmed by the experience of operating existing compression methods. The use of this stage leads to a significant increase in the computation complexity of the compression algorithms, about 20 or 40%. The second step is transformation of the image. For example, orthogonal or wavelet, as we can choose within our method, allows us to translate the original signal from the space-time domain into spectral frequency domain. In this case, the original signal, it means function of time, can be represented through orthonormal set of spectral functions in the form of a series. In addition, the use of transforming the incoming sequence of image samples allows us redistributing the image energy. Very important in our method. And also we use some indicators then help our method to build its mathematical description correctly. They are shown on this slide. A description of our method performance indicators are provided in this table. We can see discrete cosine transform, DCT, discrete Walsh transform, DWT Haar transform, our main mathematical core of our method, HT, and various wavelet transforms, WT. We can see different performance indicators values for each conversion of that we describe in different ways. And next, the specifics of our method is leads in Haar transformation method aspects appliances. To achieve our goal, we propose to use a direct two-dimensional transformation of images on the Haar basis with help of such mathematical description as 3 and 4. And we can see the main features of our formulas are coordinates of the image references, image block count, normalization coefficient, as we can see earlier, Haar transform coefficient, and submatrix, difference of matrices. When we make our experiments, we need to say that when conducting a study using the method of adapting compression of digital images in a real time, the distribution of the number of repetitions of the values of the coefficient zonal sequence ZQ was considered using the example of histogram of 3, 5, and 10 zones for test images shown in the next image in the slide. The test images were downloaded from the free internet resources. It's about 10,000 different images we built and make our experiments on this data set. The significant differences in the ZQ histogram, which are composed for all block selection zones for different images, suggest the possibility of classifying images according to the energy distributed in them with the help of 6 and 7 equations here, when E, C is energy, and Z in number of breeding zones, and K is coefficient number of in this formula. Experiment results. Based on the data we used with images and with implementation of a proposed method with the core of Haar information, we built histogram of arithmetical mean values of energy for each of our categories of images with S area of analyzing images. And we can see that the most value of energy has A and B and D categories. And dependence, also we built dependence of the compression coefficients, KCOM, on the number of excluded selection zones, W. And we can see that the last zone, J, show us the most coefficient. It means that the next, the last step of our transformations helps us to compress data about 65%. Result discussion. Significant decrease of the compression ratio becomes possible in our method with the junior zones, second and third exclusion. It's not advisable to exclude the first ZQ because we believe that because at least 90% of the image energy is distributed in it, and the coefficients have a global sensitivity. Therefore, its occlusion will introduce the greatest distortions. From the analysis of the graphing follows that during the execution of the lossy images compression algorithm, to minimize distortions of the reconstructed image, it should be excluded from the processing of the selection zones with the lowest energy. To obtain significant compression ratios, it's necessary to discard ZQ with a large number of conversion rates. It can be seen from the figures that we shown before that the most appropriate seems to be an exception from processing J, I, H, and E zones, since they have the lowest average energy, and their dropping provides a compression ratio of KCOM about 5. However, it should be noted that the root mean squared deviation for height and medium reshaped images exceeds 1.5%, already with the exclusion of J, I, and F. ZQ, which is responsible for fine details, wherein KCOM doesn't exceed more than 4 or 5 times, and distortions occur throughout the image, which doesn't allow us to choose a level of detail that can be neglected in the given processing conditions. As a conclusion, we would like to say that the method for accessing the degree of saturation of images has been developed in our research study based on taking into account the global and local sensitivity of the basis functions of the Haar transformation as a core mathematical approach of our method, using the energy index when analyzing the image transformation, which makes it possible to estimate the degree of saturation of the image with small details from the energy distribution for different images by zonal sequences. A total weighted energy index is proposed, which depends on the energy distribution and the number of orthogonal transformation coefficients, forming a zonal sequence. The scientific novelty of the presented work lies in increasing the accuracy and efficiency of the data transformations carried out during accessing the degree of digital image compression by adapting the Haar transformation for the problem under construction. The development and application of the method of adapting compression of digital images will ensure the fulfillment of the requirement for the efficiency of processing and transmission of the digital video image information in real time and accessible level of distortion of the reconstructed image. Using the technique for assessing the degree of saturation of images in our method will allow us to more accurately and compression with expert judgment to classify images, select the number of saturation classes required in each specific case in a numeric way, automate the classification process when evaluating an image, and use the adaptive compression method as a procedure. Thank you for attention.